Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 1. Today I'm going to be talking about the public switched telephone network, then I'm going to move on to broadband cable, and I'm going to conclude with a brief section on fiber optics. And with that, let's go ahead and begin this session. Of course, we begin with the public switched telephone network. Before I begin with the public switched telephone network, let's talk about what makes a WAN as opposed to a LAN. Well, as a general rule, if you own and control the line that the data is using to get from one place to another, you are not using a wide area network or WAN technology. On the other hand, if you are using a form of transmission that you don't own, as in you're leasing a line or you're paying for the use of it, then you are likely using WAN technology. One of the most common physical infrastructures used in WAN technology is the public switched telephone network, the PSTN, due to its widespread availability. Just about everybody has a telephone line being run to their house or to their building. An older technology, but still somewhat valid today for WAN technology, is dial-up. Now, dial-up utilizes the PSTN to transmit network traffic as an analog signal. Dial-up does require an analog modem to format the network traffic correctly so it can be transmitted. Your maximum theoretical speed on dial-up is 56 kilobits per second. It's not very fast. Then there's ISDN, Integrated Service Digital Network. ISDN is a digital point-to-point WAN technology that utilizes the PSTN. It's a completely digital service. It requires the use of a terminal adapter, or TA, to make the connection to the end nodes. This TA is often called a digital modem, but it's not. It's a terminal adapter. ISDN can use a primary rate interface, or PRI. Now, the PRI is composed of 23 64 kilobit per second B channels and one 64 kilobit per second D channel. That D channel is used for call setup and link management. A PRI can achieve 1.544 megabits per second speed, and that is commonly referred to as a T1 leased line. The most commonly implemented form of an ISDN, though, is the BRI, the basic rate interface. It uses only 2 B channels and 1 D channel, and the BRI can achieve speeds of up to 128 kilobits per second. Now, ISDN is not as capable as a digital subscriber line, or DSL, but it can often be implemented where DSL cannot be installed. Speaking about DSL, let's move on to it. XDSL is the term for generic DSL. DSL is a digital WAN technology that utilizes the PSTN. DSL does require the use of a digital modem. It uses a dedicated digital line between the endpoint and a Class 5 central office, or CO. Now, in order for the most basic forms of DSL to be installed, you have to be within 18,000 feet of the CO. DSL is capable of carrying voice and data. When it does carry both, filters are put in place in order for the voice signal to come through without any interference. Now let's move on to the different types of DSL. And first up is symmetric DSL, or SDSL. Symmetric DSL is synchronous in nature. That means that the upload and download speeds are the same. SDSL does not carry voice communication. So if you need voice service, an additional line is going to be needed. SDSL is used by businesses that don't quite need the performance of a T1 leased line, but they do require the symmetrical upload and download speeds. More common than SDSL is ADSL, or asymmetric DSL. It's asynchronous in nature. That means that the upload speed is slower than the download speed. ADSL can carry data and voice. Common upload speeds for ADSL are 768 kilobits per second, with download speeds of up to 9 megabits per second. It is the most common implementation of DSL in the small office, home office environment. Last up for DSL is VDSL, or very high bitrate DSL. It's asynchronous in nature as well. It's used when high quality video and voice over IP is necessary. VDSL is commonly limited to download speeds of 52 megabits per second with an upload speed of 12 megabits per second. That's a whole lot faster than ADSL. But VDSL is only possible when you're located within 4,000 feet of a central office. There is an exception to what I just told you though. The current standards do allow for up to 100 megabits per second speed over the PSTN using VDSL, but in order to achieve that, you must be within 300 meters of the central office. Now that the PSTN is out of the way, let's move on to broadband cable. Broadband cable is coaxial cable networking. It's a broadband connection to a location delivered by the cable company. Broadband cable can deliver voice, data, and television all through the same connection. And the way it works is the digital signal is delivered to the headend. This is where all the cable signals are received. The signal is then processed and formatted and then transmitted to the distribution network. The distribution network is a smaller service area served by the cable company. The distribution network architecture can be composed of fiber optic cabling or coaxial cabling and or a hybrid fiber coaxial cabling or HFC. Unlike DSL, the bandwidth of the distribution network is shared by all of those who connect to it. This can lead to increased latency and congestion during busy times. The final distribution to the premise is usually through a coaxial cable. The other thing that you need to know about broadband cable is that all cable modems and similar devices must measure up to the ISP's required data over cable service interface specification or DOCSIS specification. If it doesn't measure up, you're not going to achieve the speeds that you expect. Now let's conclude with fiber. Fiber optic networking is using light to transmit data and voice. This allows for more bandwidth over greater distances. Fiber optic networking is more expensive to install, but is also less susceptible to line noise. The fiber synchronous data transmission standard in the United States is called the Synchronous Optical Network, or SONET standard. The international standard is called the Synchronous Digital Hierarchy, or SDH. Both SONET and SDH define the base rates of transmission over fiber optic cabling, which are known as optical carrier levels. Dense wavelength division multiplexing is a method of multiplexing several optical carrier levels together, up to 32 of them, into a single fiber optic cable, effectively increasing the bandwidth of that single optical fiber. Instead of DWDM, you could use CWDM, coarse wavelength division multiplexing. It's similar to DWDM, but it only allows for up to 8 channels on a single fiber. When fiber optic is delivered to the premise, it's usually delivered over a passive optical network, or PON. A PON is a point-to-multipoint technology that uses a single optical fiber that's used to connect multiple locations to the internet. The passive optical network uses unpowered optical splitters. Now that concludes this session on WAN Technologies Part 1. I talked about the public switched telephone network, then we moved on to broadband cable, and I briefly ran through fiber optic networking. Good day, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 2. Today we're going to be discussing GSM and CDMA WAN connections. Then we're going to move on to WiMAX WAN connections, and we're going to conclude with satellite wide area network connections. There's a fair amount of information to cover, so let's go ahead and begin this session. And of course, I'm going to begin with the GSM and CDMA wide area network connections. All cellular carriers use one of two methods for connecting devices to their networks, and those methods are not compatible. Currently in the United States, AT&T and T-Mobile use the Global System for Mobile, or GSM standard, to connect their devices to their networks. Both Sprint and Verizon use Code Division Multiple Access, also known as CDMA, as their method of connecting to networks. And those two standards are not compatible. The majority of the rest of the world utilizes GSM as the method for cellular network access. Let me speak briefly about cellular networking. Cellular networking involves using the cellular phone system for more than just phone calls. Cellular networking has been around for a while, and it originally wasn't known as this, but the first version of it is 1G or 1G cellular, and it was only capable of voice transmissions. As improvements came along, we got 2G. That is cellular with simple data transmission capabilities, as in text messaging. 2G Edge offered some basic cellular networking connectivity and was a stopgap measure between 2G and third generation cellular. 3G cellular is the beginning of cellular WAN networking. It's giving way to 4G cellular, which is still an emerging technology. 4G currently consists of both LTE and WiMAX. As a special mention, we need to talk about Evolved High-Speed Packet Access, which is HSPA+. It was a stopgap between 3G and 4G networking. It's still available today. The current standard for HSPA+ allows for up to a maximum data rate of 84 megabits per second. Now, it's not quite as good as LTE, which is long-term evolution. LTE uses an all IP-based core with high data rates. Now, LTE is compatible with both 3G and WiMAX. The current standard for LTE allows for up to 300 megabits per second in download speeds and up to 75 megabits per second in upload speeds. Now let me introduce you to WiMAX WAN connections. WiMAX stands for Worldwide Interoperability for Microwave Access. That's a mouthful. That's why we say WiMAX. WiMAX was originally developed as a last-mile alternative to use when DSL or cable was not available. It can provide an alternative broadband connection to a fixed location. It uses microwave transmissions as an over-the-air method to transmit voice and data. It does require line of sight between relay stations, but WiMAX can be used to cover significant geographic distances. Also, many municipalities are exploring the use of WiMAX as a means of providing reasonably priced broadband to their citizens without having to wire every household. WiMAX is often considered to be a type of 4G technology because it is compatible with LTE networks. But WiMAX is not compatible with third generation cellular networks. It is time for us to conclude with satellite WAN connections. Satellite WAN connections are a type of microwave satellite networking. It uses microwave transmissions as an over-the-air method of transmitting voice and data, just like WiMAX. It can be an effective means of extending networks into places that are hard to reach. It does use microwave radio relay as the method of transmitting data through the atmosphere. Just like WiMAX, it requires line-of-sight relay stations, but it can cover even more distances than WiMAX. Why is that? That's because it utilizes a satellite network. By the way, because of the distances that satellite transmissions can cover, this can lead to latency problems. Think about it. The signal's got to go from a terrestrial location up to the satellite, probably over to another satellite, and then down to another terrestrial station. That's a significant amount of distance, and there's going to be some lag. I just talked about the communication satellite. They're also known as ComSats. These do form part of the microwave relay network. ComSats can use a variety of orbits, including the malignant, geostationary, low polar, or polar orbits. The low polar and polar orbits are used to boost microwave signals before sending the signal back to Earth. Now that concludes this session on WAN Technologies Part 2. I briefly talked about GSM and CDMA WAN connections. Then I moved on to WiMAX WAN connections, and then we concluded with satellite WAN connections. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 3. Today I'm going to briefly discuss Metro Ethernet WAN connections, then I'm going to move on to leased line WAN connections, and we're going to conclude with some common standards. And with that, let's go ahead and begin this session. Of course, I'm going to begin by discussing Metro Ethernet WAN connections. A Metro Ethernet connection is when the service provider connects to the customer's site through an RJ45 connector. The customer will view that WAN connection as an Ethernet connection, while in reality the type of connection will be dependent upon the level of service that has been purchased. The service provider may also use a variety of different wide area network technologies behind the scenes, but the customer will always view it as being an Ethernet connection. Metro Ethernet is commonly deployed as a wide area network technology by municipalities at the metropolitan area network or MAN level, as in at the municipal level. It's time for us to discuss leased line WAN connections. A leased line is a dedicated circuit or connection between two endpoints used for communication. When we're talking about IT, a leased line is usually a digital point-to-point connection. A leased line can utilize either a plain old telephone service line, a POTS line on the public switched telephone network, or it can be a fiber optic circuit provided by a telecommunications company. Leased lines tend to be more expensive for the customer as the circuit can't be utilized by any other entity. So the whole cost is borne by the customer because they're the only ones who get to use it. Most often the speed of a leased line is limited by what the customer is willing to pay. There are some multiplexing technologies out there that can be used to increase the amount of channels that are provided on the connection. One of the leased line technologies that you need to know about is point-to-point protocol. PPP. It is a common data link layer or layer 2 protocol that's used with leased line networks. PPP can simultaneously transmit multiple layer 3 protocols. It can transmit IP and IPX and AppleTalk all at the same time through the use of control protocols, which are actually specific to the layer 3 protocol that's being transmitted. PPP can include a feature called multi-link PPP, which allows for multiple physical interfaces to be bonded together and act as a single logical interface. This effectively increases the available bandwidth to that system. There are different types of leased line connections. In the United States, Japan, and South Korea, there are T carrier lines. Each T line is composed of 24 digital signal channels. These are often called digital signal zero channels or DSO channels. Each channel is capable of carrying 64 kilobits per second. The 24 DSOs make up what is called a DS1 channel. In Europe, we have E carrier lines. Each E line is composed of 30 digital signal channels. These are also called DSO channels. The 30 DSO channels also make up what is called a DS1 channel. When we're talking about fiber optic speeds, we often talk about optical carrier lines, or OC lines. The OC data rates per channel are established by both the SONET and SDH networking standards. SONET is the United States standard and SDH is the international standards. Interestingly enough, the OC rates are the same across the two standards. It's possible to multiplex multiple channels into the same fiber using different methods. The first method is dense wavelength division multiplexing, DWDM. It allows for up to 32 separate channels on a single fiber cable. Or you could use coarse wavelength division multiplexing, which allows for up to 8 separate channels on a single fiber optic cable. Let's conclude with common standards. The standards I'm going to be talking about are the speeds, and we begin with T lines. A T1 is composed of 24 DSO channels, which are also known as a DS1, and it's capable of achieving speeds of up to 1.544 megabits per second. If that's not fast enough for you, you can lease a T3 line. It's composed of 28 T1 lines. Now, a T3 line is also known as a DS3, and it can achieve speeds of up to 44.736 megabits per second. If you're in Europe, you might lease an E1 line. An E1 line, which is composed of 30 DSO channels, can achieve speeds of up to 2.048 megabits per second. Just as with the United States, if that's not fast enough for you, you can lease an E3 line, which is composed of 16 E1 lines, which gives you up to 34.368 megabits per second speed. While a T1 is slower than an E1, a T3 is faster than an E3. For OC lines, we have the OC1. It's capable of 51.84 megabits per second in speed. Then there is the OC3, which gives you up to 155.52 megabits per second speed. It's becoming more common now to see OC12s. With those, you get up to 622.08 megabits per second. If you want gigabit type speed, you might consider leasing an OC48. That gives you up to 2.488 gigabits per second in bandwidth. Currently at the top of the line is the OC192. That gives you up to 9.953 gigabits per second speed. So essentially 10 gigabits per second worth of bandwidth. Now that concludes this session on WAN Technologies Part 3. I briefly discussed Metro Ethernet WAN connections, and then I went on to a discussion about leased line WAN connections, and then I briefly mentioned some common standards. Hello, I'm Brian Farrell, and welcome to PACE IT's session on WAN Technologies Part 4. Today I'm going to be discussing the difference between circuit switched and packet switched networks. Then I'm going to move on to a discussion comparing frame relay versus asynchronous transfer mode. And then we're going to conclude with multi-protocol label switching. There's a whole lot of ground to cover, not a whole lot of time. Let's go ahead and begin this session. Let's begin this session by talking about circuit switched and packet switched networks. Circuit switched networks have a dedicated circuit between two endpoints that is used for communication. While set up, the circuit can only be used for communication between those ends. Circuit switched networks are most common in networks with leased line communication channels. They're best used when there needs to be a fair amount of continuous data traffic between the two endpoints. And with circuit switched networks, there is only one path for the data to take. On the other hand, in packet switched networks, data is broken up into smaller chunks and moved through the network, only to be reassembled at the other end. The data is routed using the destination address, and the data may take different paths through the network that it's traveling through. As a general rule, packet switched networks are less expensive to maintain. Why? Because the user doesn't have to maintain a dedicated circuit 24/7. They're only paying for what they're using. Now let's talk about the differences between frame relay and asynchronous transfer mode. Frame relay is a WAN technology in which variable length packets are switched across a network. Frame relay is less expensive than leased lines, but frame relay can be made to look like a leased line through virtual circuits or VCs. A frame relay network will track a VC using a data link connection identifier to identify the ends of the VC. There are two terms associated with frame relay that you should be aware of. The first is access rate. That is the maximum speed of the frame relay interface. The other term is the committed information rate, the CIR. That's the guaranteed bandwidth that a customer receives. So that's the minimum speed of that frame relay network. The access rate may be higher, but the customer is always guaranteed the committed information rate. Now let's talk about asynchronous transfer mode, also known as ATM. ATM is a WAN technology in which fixed length cells are switched across a network. These cells are always 53 bytes long. ATM can handle real-time voice and video because it's very fast, but it has poor bandwidth utilization. The small cell size reduces the efficiency of the technology, but ATM is very fast even if it is inefficient. Common speeds on an ATM network are 51.84 megabits per second and 155.52 megabits per second. Let's conclude with multi-protocol label switching. The acronym for multi-protocol label switching is MPLS. MPLS is a topology that's growing in popularity. Why? Because it's scalable. Also, it is protocol independent. MPLS can be used to replace both frame relay switching and ATM switching. It can be used to packet switch both frame relay and ATM network traffic. This allows MPLS to be used with both frame relay and ATM technologies. MPLS is often used to improve quality of service and flow of network traffic. It uses a label edge router to add MPLS labels to incoming packets if they don't have them. The label edge router then passes those packets onto a label switching router or LSR router. The LSR forwards those packets based on their MPLS labels to their final destination. Now that concludes this session on WAN Technologies Part 4. I talked about the differences between a circuit switched and packet switched network. Then we moved on to frame relay versus asynchronous transfer mode, and we concluded with a brief discussion on multi-protocol label switching.